Hi everyone. Thanks for tuning in, even if it's only because you have nothing better to do in quarantine. This video is taking the place of a regular Explore Post meeting. The topic du jour is embedded systems. If at any point in the course of this video you become confused or nauseous, pause the video until your stomach settles and then soldier on. Here's what we're going to cover today. First, an overview of what this topic even means. Embedded systems? I know both of those words in isolation, I think, but putting them together confuses and concerns me. Second, we're going to dive into the world of software engineering and learn a bit about the kinds of issues and problems that we deal with in the real world. We're going to find that some problems are easy and some of them are really, really hard. Once you're all certified armchair experts, we're going to learn in the most effective way possible, by judging other people's mistakes. We're going to walk you through a couple of case studies in software debugging that exemplify how easy or how hard it can be to track down the real source of a problem. Finally, for anyone who's left, we'll provide some cool things for you to do if you want to explore embedded systems engineering further. Spoiler alert, you will, because it's awesome. So what is an embedded system? Well, Google it, you'll find lots of textbook definitions, but here's what it really means in terms of what you'd be doing if it was your job title. It typically consists of a program of some kind being loaded, or embedded, into a microprocessor. This is a tiny, self-contained computer system. It usually has limited resources to work with, and it's usually given a narrow purpose. You can find about 100 easy examples in your car if you know where to look. There are a number of control chips that govern the engine. There are some embedded in the dashboard that control the driver's side display. There's one or two in the exhaust system that monitor the kind of gases being generated and send that data to the motor controllers to improve fuel efficiency. Each one of those chips is an embedded system in itself. At some point in time, an embedded software engineer sat down and wrote a program that would fit in the available memory space and carry out the tasks that it needed to do. So, embedded software engineers write programs. On that note, what is a program? You might be familiar with the concept already from the Python lab that we also provide, but let's take a sidebar for that thought anyway, because as with most things in embedded software, it gets a little bit more involved. It all starts with you, the engineer. Once you've figured out what you want your program to do, you type it up in your favorite text editor, and at this point, what you'd see might look familiar from the Python lab we did. The language is unfamiliar, but you can guess that it's basically just a sequence of instructions that you want the machine to follow. Now, this code might make sense to you with some practice, but as far as the computer's concerned, it's still just a text file. What we need to do next is feed the program into a compiler, which lives up to its name by compiling the code into a file that looks a little bit more like something the computer understands. In embedded software, one of the most popular languages is C. C is a low-level language, meaning that the instructions you type aren't actually too far removed from the processor's basic instructions. Something you can do in a few instructions of C will still break down into only a few more processor-level steps. What does that mean? It means we can do very powerful things with it because the instructions are so primitive, relatively speaking, that it takes the processor very little time to execute it. This means that you have a lot of control over the efficiency of your code. But what if you need even more power? We talked about higher level languages like Python and lower level ones like C. There are times, though, where you have to get things done so quickly that you literally need to control every cycle of the processor's time, and that's where assembly comes in. Assembly is a catch-all term. There's no single assembly language, because there's a different form of it for every type of processor. They all have this much in common, though. They're hard to write, and even harder to read. But they offer incredible power if you're able to master them. What you're looking at is not code that will be broken down into processor instructions. It is processor instructions. At this point, we're literally hand-feeding one instruction after another directly into the CPU. For all practical purposes, this is as low level as it gets. So, what can you do with good assembly code? Well, this. A TI-83 or 84 calculator has a Z80 processor in it. If you do your homework, you'll find out that that's the same kind of chip that powered the original Game Boy. Go ahead and tuck that one away for when you need to do some cool trivia to impress your friends. Congratulations! You have now reached conversational fluency in embedded systems and programming languages. Now that that's out of the way, it's time to talk about the main question on your mind. What do we actually do in embedded systems work? Well, the boring answer is that it varies wildly, just like any other engineering field. Even within this supposedly narrow world of embedded software, there's room for a ton of variety in what kind of work needs to get done. For a hopefully less boring answer, I'll share a little bit about what I do from day to day. There are three main components to my job: hardware support, application development, and debugging. Let's start with hardware support. Every now and then, the hardware guys come out with a new module of some kind. They spec it out to have all kinds of cool features and bells and whistles. This bad boy's got 8 output drivers, 32 digital inputs, and an Ethernet port. Beat that. Well, then it's our job to write up some code to make all that stuff actually work. Metaphorically speaking, the car's been built, but if you turn it on, nothing will happen. You still need to put something in the driver's seat. We create a layer of code just for interacting with the hardware. This serves two purposes. It lets us give the hardware guys some basic minimal code that they can use to test the module and make sure that everything works like they want it to. It also gives us a platform to build on when we go to develop a program for that module. Once the module is up and running, it's time to put some application code on it and make it do everything that we wanted it to do in the first place. This part is very open-ended and impossible to generalize. There's just any infinite number of things you could want to do with it. As an example, though, we might want to put in some code to let it talk to other modules on a shared communications network. We'd probably also add diagnostics for anything that could conceivably go wrong with the module, and make it able to report that information to the main control unit. This takes us to the third part of my job: debugging issues, also known as bug hunting, chasing gremlins, and generally losing your mind. In all seriousness, though, this is sometimes the most frustrating part of the job, but it's also the most fun part. So, let's talk about issues. The problems that we deal with mostly fall into two categories. I'm going to call one of them bugs, and the other will be errors. Let's start with errors because they're a bit simpler. You write up your code, everything looks good, and you decide to test it. You hit the compile button so you can build the program and download it onto the module, but wait, what the heck? Yeah, that's an error. We call this a compile time issue, as in when you tried to compile the program, it didn't work. Broadly speaking, errors aren't really hard to fix because you find out about them instantly. There's nothing ambiguous about it. There's a problem in the code, on this file, on this line, and you need to deal with it before you can move on. Suppose that you fix that error, and now everything's hunky-dory. You can compile the code, and it gives you a program that you can load onto the target. So you do that, and the program starts running, and it doesn't do what it's supposed to do. Maybe it doesn't give you the right data in a debug message. Maybe it doesn't make a light blink like it's supposed to. Maybe the whole thing crashes and stops running. Now, what you have is a bug. Possibly more than one. It's impossible to say until you look into it and figure everything out, and that's what makes bugs so hard. They're runtime issues, as opposed to compile time, because they only crop up when the program is actually running. Fortunately, we have tools at our disposal for debugging problems. The most important is the appropriately named debugger. Usually it's a probe that you can attach to your module and peek in on what the program is doing. Some of them are decent, like the one built into TI's Code Composer Studio. Some of them, though, are really, really good. This is the true story of how a skilled professional programmer wasted half a day debugging a really simple issue that he caused. My friend Bob, who is a real person and not somebody that I just made up, was writing a simple function, but for reasons unknown, he just couldn't get it to work. Here's what it was supposed to do. There was a loop at one point in the code that Bob wanted information about. Specifically, he wanted to know how many times it was executed. So he created a simple counter variable and added a little line like this, where every time this loop runs, it adds 1 to the variable's value. Then he could check in later with debug tools and see what number it ended up at, and this would tell him how many times it ran. I don't know why it was so important to him to know this, but Bob's a smart guy and I'm sure he had his reasons. So Bob ran his code on a module and found, much to his surprise, that the number was 1. He knew this was obviously wrong. It's like guessing the square root of an 8-digit number. You don't know what it is, but you're pretty sure it's bigger than 1. Bob spent all day racking his brains about this. He knew for sure that the loop was running more than once. What could possibly be happening that would make his variable stay at 1? Eventually, here's what he found. Bob took a closer look at the code that he added that increments the variable. Turns out he actually did it backwards. Instead of writing plus equals 1, which is a valid way to add 1 to a variable, he wrote equals plus 1, which is also a valid way of simply reassigning a value of positive 1 a bunch of times. This is a great example of a bug, because what Bob wrote at first was technically legal code, and when he compiled the program, it didn't complain at all. Plus, it looks so similar to the right instruction that unless you're specifically looking for it, you wouldn't even notice the problem. Something like this could lead to very subtle and difficult to track problems down the road. Now, I know that I promised you a couple of case studies. We're going to move on to the conclusion now, but if you're interested, stick around, and after that, we're going to take a look at a much more advanced concept. Well, that's about all we'd be able to cover in a normal session. What we've shown you here is just a tip of the iceberg view of embedded systems. There's a lot of material that we haven't even come close to mentioning, but hopefully you can see that, just like any other field of engineering, it's a very rich and varied kind of career. You could work in a single language and still have something different to do every day, and there's a lot of room for specialization. If any of this intrigues you, or if you just want to have some fun and learn a bit more about it, there are several easy ways to get started. Speaking personally, in my opinion, the single best way to start learning embedded code is to get an Arduino. They're cheap, they come with a lot of functionality right out of the box, and Arduino's version of C++ is a very beginner-friendly version of the language. There's a link in the description to the Arduino website, where you can find all their different kits and projects. That's all for now. Thanks again for tuning in, and if you have any questions, you can either leave a comment on the video or send us a message through the Remind app. We'll see you next month. If you're still watching, that means that you're intrigued by the first case study and want to see what a more advanced one looks like. Either that, or you left this on in the background, which is basically what normally happens when I talk about programming anyway, so no hard feelings. So what we're going to talk about now is not a single case study, but rather a type of bug that you might run into that really shows you what kind of environment we're working in. It's called a stack overflow. The name is pretty much exactly what it is. That'll make sense in a bit. This ties back in with what we learned earlier. Embedded programs often have very limited resources to work with. On a given target, you only have so much memory available. You use up memory by setting aside pieces of it and storing variables there. Every time you create a new variable in the code, it has to live somewhere. But you use a lot more memory than just that, and not all of it is clearly laid out ahead of time. C programs don't run for free. They need some memory space to work in. So what you do is you set up a region of memory for the system to work with, kind of like a scratch pad. We call this the stack. This is where the system stores information for running the program. It's used every time you call a function. The system stores all its working variables on the stack, enters the new function, and automatically creates the local variables of that function in the stack. Think of it like this. When the processor is in the middle of a function, it has its hands full. To jump into a new function, it has to empty its hands first and safely store what it was holding. Then it can go over to the new location and pick things up. So that's a really quick conceptual view of what the stack is and why it's important. So let me ask you this. What would happen if you had a function like this? Or a function like this that called itself repeatedly? In either of those cases, you destroy the stack. The first one asks the system to set aside a gigantic amount of memory on the stack, and the second is what we call a recursive function, meaning it calls itself an indeterminate number of times. Recursive functions are actually not even allowed in a lot of embedded software projects for exactly this reason. Because remember what we said about calling functions? Every time the system enters a new function, it has to store its current context and the new local variables on the stack. And if it does that a large number of times, like this function will, you'll run out of memory. So, what happens when you run out of memory? Well, nothing good. Anytime you have an overflow problem, the system is forced to write into what we call uncharted memory. Data is forced over top of memory space that could contain anything, and the old information is corrupted. When this happens, the system is lost, and this only ends in one way. Unpredictable behavior, usually ending with a crash. The scary part is thinking about what kind of data could be corrupted before the crash and what the program might do when it acts on it. Maybe you just overwrote a critical variable that sets the speed limit on a motor controller, and the motor it's controlling starts spinning out of control. Once you grasp all this, you can see what makes an overflow so nefarious. The behavior is always impossible to predict. You might be chasing a bug where the program crashes only once every 8 hours, when all along it turns out it's just a freak coincidence of conditions that result in a Stack Overflow happening. And if it's a more complex system, say an operating system running multiple threads, each one of those threads will have its own stack that could be broken. As a personal experience, the last time I had to fix an issue like this, it took, and this is not an exaggeration, just a bit more than a month to track it down. But that's a story for later. Anyway, for those of you who are curious and brave enough, that's a very brief look at a very advanced concept that we work with. I know this isn't easy material to learn or even to listen to someone talk about, so thanks for sticking it out this long. And again, if you have any questions, feel free to leave a comment or reach out to us on the Remind app. Thanks again for listening, and we'll see you next month.